Good morning, everyone.
Morning, sir.
Hi, am I audible to you?
Yes, sir.
Okay.
Yes, sir.
Morning. Uh, Sir is a little busy today, so he told me to engage the class for you. I thought, why not we just go through the solution of the midterm exams, isn't it? कुछ स्टूडेंट्स ने मुझे मैसेज की थी लास्ट टाइम कि कुछ क्वेश्चंस में शायद कुछ डिफिकल्टी है या कुछ कंफ्यूजन है, सो आई थॉट कि लेट्स डू सम सॉल्यूशन मिड टर्म का. ठीक है, तो मैंने क्या काम किया, आई हैव जस्ट पोस्टेड द क्वेश्चन पेपर ऑन द व्हाट्सएप ग्रुप राइट नाउ. तो उसको आप अपने
Yes,
सामने
sir.
रखो and what we'll do is we'll just go through the solutions. Okay, so first of all, just open your question papers for the midterm and we'll take questions one by one. Today is 13. Okay, all right. So have you opened the question papers?
Yes, sir.
Okay, so we'll take questions one by one and then we'll move on. Okay, let's take question first. Question first says a system is described by the state space given as follows. Find the transfer function of the system. Let me write the matrices. X dot equal to -4 -1 3 -1 x plus 1 1 u. This is the information given, and yeah, C is also given 1 0. This is the information given in the question times x, and you have to evaluate the transfer function. Okay, so you know the transfer function is given as C Si minus A inverse into B. There is another term plus D, but which is absent here, isn't it? So this is your A, this is your B, this is your C. Substitute this and you will get the transfer function. Okay, take the C, this is 1 0. I have to take the inverse of assignments A inverse. So it's just do the lambda I minus A divided by the determinant. This will be S. If the variable is S, so it's S plus 4, S plus 1, 1 minus 3. You have to find the inverse of this matrix. I just written Si minus A, okay, and B, that's 1 1. I just substituted C, Si minus A inverse. Si minus A, I have not evaluated the inverse yet, just Si minus A, and this is B. Okay, 1 0. Now inverse of this 2 by 2 matrix. First find the adjoint. The diagonal elements change their position and non-diagonal change their sign, isn't it? Divided by the determinant of this matrix. This will be S square plus 5S plus 4 plus 3 7 times 1 and 1. Okay. So please correct me if I make mistake somewhere. Okay. Okay. So let me take it here. You can do one thing, like I told you during assignments or during the class. If you can take some advantage in linear algebra. See, this entry is 0, isn't it? So this 1 will be multiplied to first row, and this 0 will be multiplied to second row. So when you pre-multiply by 1 0 and post-multiply by 1 1, what that essentially means is your let's take these two matrix vector product first. So 1 will be multiplied to row 1 and 0 will be multiplied to row 2. So this thing will be multiplied to 0. So you don't have to take this thing. That's the operation of this and this. And when you do operation of this and this says you have to take summation of first column and summation of second column. So what you have to do for product of these three is just add first two entries of this matrix. Coming back to that, this will be simply S divided by S squared plus 5S plus 7. Do you get it? Or should I show the entire steps? Yes. ये समझ में आया? What I did here?
Yes, sir.
Yes, sir.
I will repeat once again. This is, if you do this and this will be S plus 1 minus 1 times 1 and 1. This is the product of this and this. It has multiplied 0 with the second row. And when you do this and this will be simply S. S plus 1 minus 1. That's S which comes in the numerator. So, जितनी आपकी practice होगी अच्छी in multiplying matrix vectors and matrix, the whole course is dedicated for linear algebra. जितना आपका linear algebra strong होगा, you will find this course very easy. So that's question 1. This is the transfer function. Okay, S by S square plus 5 plus 7. And I guess you have been using MATLAB these days, which students in MATLAB really हैं. So a good exercise is to try these things in MATLAB also. In MATLAB, what you can do, you can store this A matrix, you can store B matrix, you can store C matrix, first of all, from the question. Okay. Then in MATLAB, you can type simply state space to transfer function. Let me write state space to transfer function. A, B, C, and D. And this will be stored in numerator and denominator. If you type this command in MATLAB, but before that you have to store A, B, and C. Okay. Or let me just write the entire thing. This will be -4, -1, 3, and what's -1? You have to store B as well, 1 and 1, and you have to store C as well. C is what? 1, 0. Okay, these are the three commands. When you store ABC, you type this command, ABC, D is 0. These information is not given. So when you store this command, MATLAB will give you the coefficients of numerator polynomial and the coefficients of denominator polynomial. So it will give your n will be equal to 1. No, it will not be equal to 1. It will be like this, 1, 0. And your D will be 7, 5, and 1. This is basically the coefficient of s to the power 0. This is coefficient of s to the power 1. This is coefficient of s square. This is how it works. So this is basically s square plus 5s plus 7. And this is s plus 0, s. Okay? So you can do like this as a MATLAB, and this will give you a transfer function. Okay? You can verify this. Okay? But you should be able to know how to evaluate it using hand, because for simplistic systems like 2x2 systems or 3x3 systems, you should be able to do it using hand. Because Zada matrix vectors, it's very simple. And you have to remember the information that coming from B and C. If it's sparse, you have some values as zeros, then it becomes very easy. Okay, so that was question 1. Coming to question 2 now. Question 2 was for the system given with UT as unit step and 0 initial state, find YT. Again, this question was to find solution of state space. You're having 2, 0, 0, 4, x plus 1, 1, u, x dot. And other information that's given y is 4, 0. 4, 0, x. And information is that u is a unit step. This information is given. What else? zero initial conditions. I should not write 0 here. I should write t0. X of t0. Whatever is the initial time, at that time the value of x is 0. This is your A, B, C, and we have to evaluate the yt. Find yt. So what's the solution of yt? Or before that, let's write xt. What's the solution of this state space equation? आपने काफी बार किया है. Some t naught to t, e to the power a t minus tau, b u tau d tau, isn't it? This is the solution of the state space equation, of the state space model. So you have to solve this equation for these matrices and vectors. यहाँ पे your xt is 0, which means this term is 0. Okay, this term is 0, so you just have to evaluate this integral. That will give you x. When you get x, you have to multiply with c, and you will get y. Okay, so let's find out x. xt. Let's find out this integral. This goes from initial condition is taken as 0. Which means that you have to take initial time as 0 and final time as t. And e to the power 8t minus tau. यहाँ पे जब सच आपको ये पढ़ाया होगा this equation, the major जो आपका computation होता है, that goes in solving e to the power 80, isn't it? सारा computation goes to e to the power 80. ठीक है. अब यहाँ पे e to the power 80 जो है, that's outside the integral as well as inside in the integral. तो यहाँ पे तो ये 0 हो गया. अब यहाँ पे you again need e to the power 80. ठीक है. अब it depends how you evaluate e to the power 80. It depends upon the question at hand, and it depends upon a. See, your a. The advantage here is that this is in diagonal form. Your a matrix is a diagonal term, and the advantage here is for diagonal matrices, it's very easy to evaluate e to the power 80, isn't it? If you have a diagonal matrix A, let's suppose lambda 1, lambda 2, and you have to find, this is A, and you have to find e to power 80, it simply becomes lambda 1t e to power lambda 2t. और ये चीज आपने पढ़ी है. If you have a diagonal form, there are some techniques which first diagonalize your A, and when you diagonalize A, then it becomes very easy to find exponential of that A. Simply जो diagonal terms होंगे उसमें exponential आ जाता है, और non-diagonal तो always 0 है ही. तो यहाँ पे matrix is already in diagonal form, so the eigenvalues are 2 and 4. You don't have to evaluate eigenvalues for this; they are sitting right there, 2 and 4. So what's e to the power 80 minus tau? This will be a matrix, isn't it? So it will be e to the power this 2t minus tau, 0, 0, e to the power second eigenvalue, or the second diagonal entry, 4t minus tau. That's your e to the power 8t minus tau. The variable t जो है यहाँ पे variable t minus tau है. I'm supposed to instead of t, I'm supposed to t minus tau times this b. B is 1, 1. Times the u tau. U is a unit step. Okay, that will be taken as 1, because for unit step u of t equal to 1 for t greater than 0. You know this for a unit step. As time increases beyond 0, the value is 1. Why is it 1? Because it's a unit step. The information is a unit step, that's why it's equal to 1. So you have to just multiply with 1. So you have to evaluate this integral. That will give you xt. Let me just erase this. यहाँ पे लेते हैं. This is again matrix vector. You have to multiply 1 and 1. So this will extract this entry. This will extract this entry. This will be 0 to t. e to the power 2t minus tau e to the power 4t minus tau d tau. I have not solved the integral yet. I have just multiplied this term with b. So matrix vector in terms of diagonal becomes easy. Just the first entry and second entry gets extracted. Okay, that's equal to your xt. Okay. We will not yet solve the integral because we know this is not the complete solution. The complete solution is yt, and that's equal to c times xt. And we will take advantage what c is. What's c? C दिया है क्वेश्चन में. हाँ 40 times this thing 0 t e to the power 2t minus tau e to the power 4t minus tau dt. D tau. Tau is a variable here. So again, one entry is 0. That gives an advantage that this term, we don't have to evaluate this term. We only are interested in e to the power 2t minus tau. So, and that whatever comes, it will be multiplied by 4. So let's evaluate this integral now for first entry. When you do the integration, this will be what? Minus 1 over 2 e to the power 2t minus tau. There's a bracket here, and the limits are 0 and t. And this thing has to be multiplied by 4. This will multiply by 4, this will be multiplied by 0. So I have not taken this thing, I have just taken this thing. And when you do the integration with respect to tau, the coefficient of tau is 2. That's why coefficient of tau is minus 2. That comes down 1 over 2, and rest, everything remains same. And I have not substituted the limits. Now we'll substitute the limits. This will be minus 2. Substitute first tau t. This becomes 0. So this comes to be 1 minus substitute 0. It becomes e to power minus 2t. Yeah. Or you can write simply 2 e to power minus 2t minus 1. I'll just absorb this minus inside. So that's your solution. Any questions in this? Yes.
Excuse me, sir.
Yeah.
Sir, मतलब हमने ये मतलब मैंने ये questions किया and I got the same answer but using a different approach.
Yeah.
Like first we find the transfer function that is g of s. उसके बाद we found out y of s जो हमने निकाला g of s को multiply किया u of s. U of s was 1 by s because it was a unit step input. Then we applied inverse Laplace on y of s. फिर हमें y of t मिल गया. So is it correct?
Yeah, it's correct. Basically, आपने क्या किया है? There are two techniques to solve a system, the dynamical system. In the introduction, we have discussed two techniques. One is a time domain technique, another is a frequency domain technique. Here we are using time domain technique. So because we using the variable t, that's why we are in state space. What you have used is a transfer function modeling. So that's a frequency domain technique. Both of the techniques will give you the same answer. If you do the transfer function, then evaluate xt, then yt, that's again the same. And if you go in this way, this will also give the same answer. Okay. So there are a couple of methods to tackle a problem. Okay, coming on to question number 3. It's also better if जो आपके solutions आपने जो upload किए थे, if you take it out right now और आप देखो कि आपके solutions match हो रहे हैं कि नहीं, और आपको पता चलेगा कि किस step पे wrong हुआ है. अगर कहीं पे गलती है, you can find it out right now. ठीक है. Question 3 was again a 2x2 system. Initial condition, find the state transition matrix. So state transition matrix जो है, it's very important in this course. Either it comes directly as a question or gets involved in another question. So इसकी काफी practice होनी चाहिए आपको to find e to the power 80, especially for 2x2 systems. So let me write the dynamics. 1 minus 3 x plus 1 0 times u, and what else? x0, that's minus 1 3 transpose. Okay, find the state transition matrix e to power 18. Okay, you can use any method to find e to the power 80 because it's not mentioned in the question which method you have to use. You can use any method you like. Okay, so let me just solve it using the standard method जो हम use करते हैं. E to power 80 Laplace inverse of Si minus A inverse. I'm using this technique. I'm evaluating Si minus A, finding its inverse, and finding the Laplace inverse of the whole to get e to power 80. Okay, so let's just break it down. First of all, Si minus A of this matrix. This will be S plus 3 minus 1 0. Okay, ये चीज आपको आनी चाहिए without solving the whole Si minus A. Okay, as a how I remember it, the diagonal entries है subtract S minus 0, S minus of minus 3, that's S plus 3. और जो non-diagonal है just change the sign. 1 comes minus 1 and 0 becomes 0. So that's your Si minus A. Or lambda I minus A, whatever variable you use here, the matrix comes out to be same, okay? This is Si minus A. And now I have to find its inverse, which is equal to what? Again, for inverse, you have to find the adjoint. S plus 3, S, 1, 0, divided by the determinant. This is what? S square plus 3S. Or let me just write it as like this. S into S plus 3. Okay. So this is your Si minus A inverse. This is your Si minus A inverse matrix. I have evaluated. Now what I have to do? I have to apply the Laplace inverse of this whole thing. Before I apply Laplace inverse, what I can do, I can divide this thing for each entry. What's this by this? That's 1 upon S, isn't it? 1 divided by S into S plus 3. This is 0. This is 1 by S plus 3. Okay. I just divided every entry with 1 by S plus 3. And I have to find the Laplace inverse of this. You can do partial fractions for this term. That will be easy to evaluate Laplace inverse. If you do partial fraction of this denominator, there will be A by S plus B by S plus 3. Finding the coefficients, you can replace it by, I have written it here, 1 by 3, 1 minus, 1 by S. It's 1 by S plus 3. If you find the partial fractions quickly, A comes 1 by 3 and B becomes minus 1 upon 3. You can take 1 by 3 outside, and this is a partial fraction. Now take the Laplace inverse. Laplace inverse of 1 by S, that's 1. Laplace inverse of this, 1 upon 3. This is 1 minus e to power minus 3t. This is 0, and this is e to power minus 3t. That's your e to power 80. Okay, so you could have used any method you like. So this is your answer, 2 by 2. This was question number 3. Quickly moving on to question 4. What was question 4? Okay, consider a system. Initial conditions दिए हुए हैं. Alpha and beta are the 2 eigenvalues. Okay, so You are given a system x dot question 4. You are given a system x dot equal to ax, a linear system with no excitation, no input term. Eigenvalues. This is a question on basically eigenvalues. Okay. No, this is not a question on eigenvalues. This question uses the information from eigenvalues. Eigenvalues are lambda 1 and lambda 2. Okay, this is the information given. And one more information is that these are distinct. This is a very important hint given in the question. Okay, हमने देखा है during the course कि when the eigenvalues become repeated, some things change. But here we are given that these are distinct. Okay, so it becomes very easy now. So find response xt. You have to find xt due to initial condition x0 equal to alpha. And alpha and beta are the eigenvectors of the problem. This is also given. Okay. So alpha and beta are the eigenvectors corresponding to lambda 1 and lambda 2. And the first eigenvector, alpha, that's your initial condition. For this system, you have to find xt. Is there anyone जिसने ये question solve नहीं किया है, जिससे ये question solve नहीं हुआ? How will you approach this question? See, you have to find xt, and you know the xt, the expression for xt. वही जो हम लिखते हैं, plus the integral part. Here, let me just write it. जो हमने पिछले क्वेश्चन में यूज किया ना, some t not a t. See, the expression for xt is a summation of two terms. Okay, this first term is coming from initial conditions only. The second expression is the forcing part. We call it the forcing part. Why? Because this is the dominant force is coming from the input, and this for this solution, the dynamics are being excited by the initial conditions. So for a question, if there are no inputs, this term goes 0. So the overall xt is being supported by initial conditions. On the other hand, if initial conditions are 0, then the whole solution is being dominated by your input. Okay. For this question, there is no input. So this thing goes 0, which means that your state will evolve only using the initial conditions. This was an extra information. Okay. So just substitute this and you will get xt. E to power at times x0, and x0 is alpha. For that, we need e to power at. Again, it's coming again and again in every question. A is not given. A is not given, but eigenvalues are given, and they are distinct. This is an important thing. In the previous question, I told you if you are having two eigenvalues which are distinct of this A matrix, how will you write this e to the power at? You can simply write it as e to power lambda 1t, e to power lambda 2t, 0 and 0. Isn't it? If you know the eigenvalues of A, which is lambda 1 and lambda 2 in this case, and they are distinct, you can simply write e to power at as like this. No evaluation needed, because we know eigenvalues. And here they are lambda 1 and lambda 2 times x0. What's x0? That's alpha. I can write it like this. No, x0 is alpha. That's not a scalar. This is a vector. Alpha is a vector. I cannot write it like this. Alpha is itself a vector. So times simply alpha, because alpha is itself a vector, isn't it? Alpha is an eigenvector. So alpha can be alpha 1, alpha 2, like this. So I'm using alpha. So what's your solution? It's simply, if I assume a structure like this, if I assume the components of this, then it becomes alpha 1, alpha 2. And your solution becomes alpha 1 e to the power lambda 1 t plus alpha 2 e to the power lambda 2 t. If I have assumed my structure like this, if I don't need to assume a structure like this, I can simply write alpha e to the power lambda 1 t. Is that the answer? Yeah. Or this is a more general representation. So I prefer to use this. So the point in this question is the eigenvalues are given, lambda 1, lambda 2, and that information is being used to evaluate e to power 80 times your initial condition. And initial condition in this case is alpha. So if I just writing the components of alpha is alpha and alpha 2, then I can multiply and get the equation. Is it okay? Okay.
Sir, if we write it like alpha and 0, जैसे आपने पहले लिखा था,
If you write this as alpha and 0, if you write like this structure, then
we get only the first term, na?
Yes, then you get the first term. Then this is your solution. Both of the ways are correct. If you write it like this, then this is the answer. This is also right. If you write alpha like this is also right. ठीक है, दोनों तरीके सही है.
Okay, sir.
Okay, moving on to question number 5. Q5. You are given a 3 by 3. By the way, this is the only question in which a 3 by 3 system is given, isn't it? बाकी जितने भी हैं उसमें mostly 2 by 2 ही है. Yeah, question 10 is also 3 by 3. So let's see what it says. -1 0 0 2 0 and last column is -1 0 and -2. This is A. And you have to evaluate this thing. A cube minus A square minus 4A plus 5I. So this is a matrix polynomial. B is a matrix and its value is A cube minus A square plus minus 4A plus 5I, where A is this and I is the identity matrix. Okay. You have to find the determinant of B. Find determinant of B. Okay, so the first thing that comes to mind is you just do A cube, substitute here, A square, 4A and 5I, solve this entire thing, you get the B, find the determinant. But you will not use that thing because that's not an efficient way of solving this. What you will do, you know Cayley-Hamilton theorem. And Cayley-Hamilton theorem allows you to solve matrix polynomials of any order. अगर आपको Cayley-Hamilton theorem अच्छे से आती होगी, then you can evaluate not only this polynomial, any polynomial in A. That will give you B. And then you have to find determinant of B. This question has basically two important informations. First is how you will evaluate B, and do I need to evaluate B first? Because I need only the determinant of B. I don't need the entries of B. I just need the determinant of that. So one thing that you can use is information from the eigenvalues of B. You know the determinant of a matrix. Determinant of any matrix. That's equal to product of eigenvalues. So this is a theorem or a fact that you can remember. So if I know the eigenvalues of B, I will just, first of all, what will be the dimension of B? The dimension of B will be 3 by 3, isn't it? Because this expression will solve, this will get a 3 by 3 matrix. So this is a 3 by 3 entry, it's a 3 by 3 matrix, it will have 3 eigenvalues. Okay. If I can obtain the 3 eigenvalues, I can do the product of them and I will get the determinant of B. Let's find the eigenvalues of B. Okay. So, and we will use Cayley-Hamilton to solve such kind of questions. Okay, so A is given. The first thing that comes to mind is finding the characteristic polynomial of A. This is lambda I minus A. Again, the same thing, lambda minus 1, lambda minus 2, lambda plus 2, 0, 1, 0, 0, 0, and 1. This is your lambda I minus A matrix. But the characteristic polynomial says you have to take the determinant of this matrix, not the matrix, take the determinant of this matrix and set that equal to 0. That will give you the solution of this equation. Okay, so that's your lambda I minus A. And I have to take the determinant of this matrix and set it to 0. I will get this lambda. Okay. Again, I'm using the advantage of symmetry here. You can see that if I expand this determinant, I will simply get lambda minus 1, lambda minus 2, and lambda plus 2 equal to 0. No need to solve the entire thing. Why? Because when you expand about this, you get lambda minus 2, lambda plus 2, which is here. This pivot is already 0, no need. And when you solve for 1, you eliminate this and this. Again, you're having zeros and zeros here. So when most of the entries are 0 in a matrix, it becomes very easy to find any operation. Let it be determinant, let it be inverse. Okay, so from that, you can quickly get the eigenvalues. Minus 1, 2, and minus 2. These are the eigenvalues of A. These are the eigenvalues of
Sir, 1, 2, minus 2.
Sorry? Yeah, 1, 2, minus 1. Thank you. This is 1, 2, and minus 2. These are the eigenvalues of A. And we will use this information to evaluate eigenvalues of B. Because A and B are related by this expression. So the information I'm extracting here from the question is if I know the eigenvalues of A, from that I can evaluate eigenvalues of B. And once I have eigenvalues of B, I can use this thing. The product of those eigenvalues will be determinant of the matrix B. Okay. So how will you find the eigenvalues of B? I will just remove this expression. These are the eigenvalues of A. Okay, the first eigenvalue of B, because we know B will be having 3 eigenvalues. So let me just here write first eigenvalue of B. You know Cayley-Hamilton theorem. Every Cayley-Hamilton theorem basically says every matrix satisfies its characteristic polynomial. And there are 2 versions of Cayley-Hamilton. One is matrix polynomial, another is scalar polynomial. आपने देखा होगा. So matrix polynomial में every matrix satisfies its characteristic polynomial, and every eigenvalue satisfies its scalar polynomial. So if I write I'm interested in eigenvalues, so I will be substituting each eigenvalue corresponding to the scalar entry A. So first, let me take first eigenvalue of A, that's 1. And I will substitute it here. 1 cube minus 1 square minus 4 times 1 plus 5. 5i, in case of scalar, this is 1. And when I take a scalar polynomial, then here it's not A, it will be the first eigenvalue. Scalar polynomial will look like this: lambda cube minus lambda square minus 4 lambda plus 5. This is a scalar polynomial in lambda. And I am substituting the first lambda. That's 1. Okay, this is how I will solve this. So this will come out to be what? This will be simply 1. Okay, quickly, second eigenvalue of B. Second eigenvalue of B, substitute the second eigenvalue corresponding to, let's say, 2. 2 cube minus 2 square minus 4 into 2 plus 5. This is how much? This is again 1. Okay, third eigenvalue of B. Substitute minus 2 now. Minus 2 cube minus 2 square minus 4 times minus 2 plus 5. This is also 1. So the 3 eigenvalues are 1, 1, and 1. So the determinant of B is the product of the eigenvalues, which is 1. That's your answer. Another approach, जैसे मैंने start में कहा था, another way to do it is to solve this entire matrix thing. But for examination purposes, you will avoid that, क्योंकि आप पूरा solve नहीं करोगे, because you have to find a cube. और यहाँ पे ये problem होगी. Had it been another polynomial, let's say a to power 30, 21, what will you do? You cannot practically solve this thing. You cannot practically multiply 30 times. So you use Cayley-Hamilton theorem. You find the scalar polynomial, and if you know the eigenvalues, you can simply take lambda to power 30 minus lambda to power 21, which will be easy because the eigenvalues are simply very low. So that's the advantage of finding eigenvalues. You can find the exponential quite easily. You can find any polynomial quite easily. So that's the information from this question. Moving on, question 6. Zero, 1 minus 6 minus 5. Again, e to power 80. So, काफी repetition हो रहा है. Using Cayley-Hamilton. Find e to power 80 using Cayley-Hamilton. In this question, it's specifically mentioned to use Cayley-Hamilton theorem for this question. Okay. So characteristic equation lambda I minus a, that's equal to lambda plus 5, and just reverse the sign of this. That's equal to lambda I minus a. Okay. Now find the determinant of lambda I minus a and put it equal to 0. So that will be equal to lambda square plus 5 lambda plus 6. So minus 2 minus 3. These are your eigenvalues. Okay. And remember the fact I told you product of eigenvalues equal to determinant. What is the determinant of this matrix? Determinant is 6. That's the product of these two. Okay. So I have found the eigenvalues, and I have to use this information to obtain e to power 80 using Cayley-Hamilton. So Cayley-Hamilton says since a is second order polynomial, so I can write g of lambda as beta naught plus beta 1 lambda. Okay, ये आपने पढ़ा है क्लास में कि scalar polynomial corresponding to a second order polynomial, second order matrix is given by beta naught plus beta 1 lambda. So quickly substitute the two values. G of lambda 1, that will be beta naught plus beta 1 lambda 1, and G of lambda 2, because we're having two eigenvalues, is equal to beta naught plus beta 1 lambda 2, and lambdas are minus 2 minus 3. Substituting minus 2 first. And what's the polynomial? We are finding e to the power 80. You have to keep that in mind. So e to the power lambda is minus 2. Minus 2t is beta naught minus 2 beta 1. For this thing, minus 3, e to the power minus 3t, beta naught minus 3 beta 1. So two equations, two variables. You can get beta naught and beta 1. Okay, let me just write beta naught and beta 1 values. 3 e to the power minus 2t minus 2 e to the power minus 3t, and beta 1 will come out to be e to the power minus 2t minus e to the power minus 3t. This is simply I just eliminated. If you just subtract this from this, will eliminate beta naught. Once you eliminate beta naught, you can get beta 1. Once you get beta 1, substitute back, you'll get beta 1. So these are your values. And you can use these values here. once you have find out beta naught and beta 1. This was a scalar expression. Corresponding to that, you'll be having a matrix expression, which will be e to power at equal to beta naught I plus beta 1a. This is your matrix expression corresponding to this. Beta naught I, because this will be another, this is a vector times a matrix plus beta 1 times your, instead of lambda, I will use a. That's how you get e to power at. Now, substitute beta naught beta 1. We have already evaluated beta naught beta 1. This beta naught gets multiplied with I. So I can write it like this. 3 e to power minus 2t minus 2 e to power minus 3t. This is 0, 0. Again, the same thing. 3 e to power minus 2t minus 2 e to power minus 3t. This whole expression is beta naught I plus beta 1 times a. This is e to power minus 2t minus e to power minus 3t times your a. A is 0, 1, minus 6, and minus 5. Okay, so just do the summation and you will get your e to power at. This is 3 e to power minus 2t minus 2 e to power minus 3t. This is 0, 0. 3 e to power minus 2t minus 2 e to power minus 3t plus you have this thing. Multiply each entry with this. This is 0. E to power minus 2t minus e to power minus 3t times this will be minus 6. Yeah, minus 6 e to power minus 2t or plus 6. Yeah, plus 6 e to power minus 2t with the last entry. Last entry multiple minus 5. Minus 5 e to power minus 2t plus 5 to power minus 3t. This takes a little bit of exercise. So do the addition. This plus 0 is 3 e to power minus 2t minus 2 e to power minus 3t. 0 plus this thing is e to power minus 2t minus e to power minus 3t. 0 plus this is again this. Minus 6 e to power minus 2t plus 6 e to
Excuse me, sir. Sir, वहाँ
Yeah.
ऊपर minus 6 e to the power minus 2t plus 6 e to the power minus 3t.
Yes, thank you. This is 3. This is 3. Yes. And do this addition. Minus 2t minus 2t. Minus 5 plus 3 gives minus 2. Minus 2 e to power minus 2t. Again, minus 3t minus 3t. Compare the coefficients. 5 minus 2 gives you 3. 3 to power minus 3t. That's your e to power 80. Using Cayley-Hamilton. See, Cayley-Hamilton took a lot of steps. इसमें scalar polynomial निकालना है, beta naught, beta 1 निकालना है, and then you have to do this. But again, it's a 2x2 system. A lot of things becomes easier because again you have having a 0 entry here. Okay. So e to the power 80 is again coming for every question. Question number 7. Given a system, obtain a state diagram. Minus 2, 1, 1, 1 minus 2, x plus 2, 1 u. By the way, I'm moving very fast because time is getting short. So if you're having any doubt, you can, when we upload the video, you can just pause the video, solve it, and move step by step. Okay, I'm here moving a little bit fast. Obtain a state diagram in signal flow graph. You have to obtain a state diagram. Let me write it component wise. This means x1 dot is minus 2x1 plus x2 plus 2u. I'm just expanding the terms. And x2 dot is x minus 2x, x1 minus 2x2 plus u. I just expanded this matrix. So, couple of ways to do it. Let me just try one thing. Signal flow graph use karna hai. Let me just draw a couple of nodes. Let me take it as x1. This is S inverse. So this will be x1 dot, isn't it? And x2 S inverse. This will be x2 dot. Okay. See the first expression. What first expression says? First expression says x1 dot, which is here, this node, that's equal to minus 2 times x1. x1 is here. So minus 2 times x1 plus x2, which is here, 1, minus 2 times x1 plus x2 plus 2u. Let me write u here. Plus u, which means I have to take a tapping here. No, not here. Here. With a gain of 1. So see this x1 dot, 2x1,
So 2.
minus 2x1 plus 1 times x2 plus 2u. This is 2 plus 2 times u. x1 satisfied. x2 dot is here. That's equal to x1, which means x1 is coming here, 1 minus 2 times x2. x2 is here. Minus 2 times x2 plus 1 times u. Okay. If you have enough practice, you can straight away write this. Or one by one, just see entry wise and write the nodes and try it a couple of times and you will get it. But agar aap practice achhi hai, so you can write it straight away. Okay. Question number 8. Question 8 says minus 4, minus 3, 1, 0. Open eigenvector matrix P and hence diagonalize the matrix A. Again, eigenvalues and eigenvectors are coming. So eigenvalues are minus 4. No. Just solve it. If you are not sure, eigenvalues equal to lambda I minus A equal to 0, which is lambda plus 4, lambda plus 3, minus 1, 0 equal to this. Yeah, it comes out to be same. Lambda plus 4, lambda plus 3 equal to 0. Minus 4, minus 3. This entry was 0, so ये करने की जरूरत नहीं थी. Minus 4 and minus 3 are eigenvalues. Now find the eigenvectors. This question is based on eigenvectors basically. So a couple of ways again to find eigenvectors. We will here use adjoint of lambda I minus A. Why? Because I have already obtained lambda I minus A. So taking its adjoint is very easy. Its adjoint is lambda plus 3, lambda plus 4, and this goes 1, 0. Isn't it? Change the diagonals, change their position, and non-diagonals change their sign. That's your lambda I minus A times your eigenvector. No, we don't have to take the eigenvector. This is your adjoint of lambda I minus A. You have to now substitute your lambdas one by one, and you will get the eigenvector for each entry. Substitute minus 4 for minus 4. Substitute minus 4 here, it will become minus 1, 1, 0, 0. So you can take any column now. I'm skipping a lot of things here, okay, because I know that you know some things. You can take any column. Let me take this. So your first eigenvector, let me just write it as 1 equal to 1, 0. This is corresponding to eigenvalue minus 4. Corresponding to lambda 1 equal to minus 4. Okay, we can take any column of this lambda I, adjoint of lambda I minus A. And eigenvectors give you a direction in the state space, and the expansion or shrinking that given by lambda. See, you can ask you, we can take -1, 0 also. Quickly, if I show you, 1, 0 direction is this, and -1, 0 direction is this. So again, it's the same direction, whatever you take. That's the meaning of you take any column. Okay, substitute now the second eigenvalue for lambda equal to -3. For -3, it becomes 0, 1, 0, and 1. Okay. Again, take any column. See, taking a 0, 0 is a trivial solution. You cannot take 0, 0. 0, 0 is not a direction. 0, 0 is no direction. You can take 1, 1. That's your eigenvector. So your second eigenvector is 1, 1 corresponding to eigenvalue -3. So what's your P now? P is just you just take your eigenvectors and stack it as a columns in this P. So first eigenvector was 1, 0. Second eigenvector was 1, 1. This is your matrix, which will transform your A into diagonal form. And quickly you can find P inverse. What's P inverse there? 1, -1, 0, and 1. This is a P. This is a P inverse. Now you have to find your diagonalized matrix. That's expression given as P inverse AP. You have P inverse, you have A, you have P, and you can find your diagonal matrix. By the way, this will be simply a matrix with eigenvalues on the diagonal. -3 pehla tha, and second eigenvalue was what? No, -4. You don't even have to evaluate this. You don't have to evaluate this because you know जो diagonal आएगा, इसकी entries the eigenvalues ही होंगे. ठीक है? Question 9. S cube plus 8s square plus 17s plus 8 upon s plus 1, s plus 2, s plus 3. You have to find the construct state models for each of the transfer function in different canonical forms using an inspection. First, companion form. Just by inspection. You know, first companion form 0, 0, 1, 0, and what? 1 here, 0 here, and the last row is okay. First of all, s cube plus 8s square plus 17s plus 8. Just product this. This becomes s cube plus 6s square plus 11s plus 6. Just the coefficients in reverse order. Coefficients of the denominator polynomial written in reverse order. What's B? For first companion form, it's always 0, 0, 1. What's C? This is a proper transfer function strictly because it's cube and cube. So 8 minus 6 times 1, that's 2. 17 minus 11 times, this is coefficient 1. 17 minus 11 times 1 is 6. And 8 minus 6 times 1 is 2. 262. That's the first companion form. What's the second companion form? Second companion form is just the transpose of this. So the matrix C is in second companion form. Let me write it A2. That's equal to A1 transpose. Your B2. And this 2 subscript denotes second companion form. That will be simply C transpose. And your C2, that will be your B transpose. So these are your 2 companion forms. Now the Jordan's canonical form. For Jordan's canonical form, you have to obtain what? You have to obtain the pole residue form. If you obtain the pole residue form, s cube plus 8s square plus 17s plus 8 divided by s cube plus 6s square plus 11s plus 6. Quickly, if you find the pole residue form, it comes out to be minus 1 upon s plus 1 plus 2 upon s plus 2 plus 1 upon s plus 3. This is basically the partial fraction expansion of this. So A, B, and C. Quickly. In Jordan's companion form, you know this will be 1, 0. This will be here 0, 0, and 0. And this will be here 1. So you just have to fill the diagonal entries. This is a base matrix. Diagonal entries are just the poles. Minus 1, minus 2, minus 3. With it written in negative sign. Minus 1, minus 2, minus 3. What's B? B is a distinct poles, isn't it? 0, 0, 1. What about C? C are the residues. Minus 1, minus 1 or 1? Minus 1. Minus 1, 2, and 1. This is your Jordan's form. And D is equal to 1. आपकी कोई क्लास है अभी 11 बजे?
Yes, sir.
Okay, we will just stop here. अभी हमने we have reached question number 8. Question 8 or 9? This was 9th. This was question number 9. We are just short of one question. So, do you want me to continue, or we'll just do that question on the next class? Quickly. Should we do the question number 10, or we'll just stop here?
Sir, we will do it in next class.
We'll do it next class? Okay. Yes. Okay, well, question number 10 will be done the next class. So, thank you for today. You can leave for the next class, okay? Thank you.
Sir.
Wait.